It's my pleasure to introduce Dr. Jessica Flack, who is joining us for two talks, one today here, and tomorrow is at the Marshak Colloquium at 3 p.m. In the Young Research Library. She is currently at the C4, the Center for Complexity and Collective Computation program, co-directs that at the University of Madison, Wisconsin, but is on her way back to Santa Fe, where she'll direct that program there. She received her PhD at Cornell, or a PhD at Emory, rather. And I sort of first discovered her, what I'll say, I think are some really seminal work as part of her dissertation, where she was looking at social relationships and how social relationships using network statistics can be modeled and knocked out both statistically and really with groups of captive animals, in this case thumbtail macaques. And you can begin understanding how social relationships, particularly male third-party policing, stabilizes groups. Her work capitalizes on a pretty impressive quantitative computational toolkit to ask a variety of questions about animal and human behavior. Yes.
Well, thank you guys so much for coming. Thank you, Dan, for inviting me here. It's a pleasure to be here in Southern California. The kinds of things in nature that fascinate me are these kinds of things where you have amazing aggregate level patterns and function arising from the interactions of components with only partially aligned interests. And of course, most of the social has been on functional questions. So what's the benefit of living in groups? Why do we cooperate? All this. And there's been much less attention to the question of how these kinds of structures arise in nature. And of course, that's traditionally the domain of pattern formation, and there's, of course, work in evolution and development on those kinds of questions. But there hasn't been so much in social evolution. The emphasis really there has been on the functional questions, on the cost and benefits of aggregating. And today I'm going to talk about how we can start to think in a principled way about those how questions, about the emergence of structure and function at one level up. And I want to introduce first, to sort of ground the discussion, a concept called social niche construction, which is built on some of the work of John Elingsky, Kevin Leland, and Mark Feldman, who themselves built on Richard Dawkins and Lewinson, of course. And they introduced ecological niche construction. Probably familiar with that idea. Social niche construction is something we introduced in our 2006 paper on policing. And we define it as construction of environmental variables such that the modified variable has functional consequences. Usually we talk about reduction of uncertainty, for the constructor and his offspring through learning or evolutionary dynamics. And so we're talking about social variables. And in the social case, the construction is typically of institutions or social structures. So like spatial structures like that fish school counts as well. It has the additional feature of being collective, and the modification may be in terms of changes to time scales, space scales, robustness, sensitivity, or trajectory in phase space. Now, this is a sort of schematic of niche construction, social niche construction, that we modified from a schematic that John put together a long time ago. And the basic idea is you have strategies or behavioral variants, and those behavioral variants, those individuals forming those strategies collectively produce their social environment. The social environment is inherited, it persists, it's got some time scale, and it can affect the next generation of individuals. And there's a so the construction process is this feed-forward process, and then there's a learning or selection process that feeds back. And mostly I'm going to be talking about the construction process, which has received relatively little attention, as I said. And I'll focus a little bit, too, on selection and learning, insofar as the individuals, as they produce these social environments, are using the structures that they produce. They're using estimates of those regularities that are arising from the interactions to guide their behavior to help them choose among their strategies. And the other thing I want to emphasize, too, is as Kevin recently pointed out to me at a meeting at SFI, most of the work that he's done and his collaborators have done on niche construction is focused on the individual. We focus very much on collectives, so the role of individuals jointly constructing the social environments that they live in. So in our work, we proposed that biological systems are information hierarchies. I'm going to talk about this tomorrow, resulting from the collective effects of components estimating regularities in their environments by coarse graining or compressing data and using these coarse grainings to tune their strategies to better predict the future. And if you think that biological systems are these information hierarchies, then a natural approach is to treat that micro to macro mapping, microscopic behavior, the individual or component level, macroscopic, those social structures they produce, as a collective computation. Okay, and the system search for configurations that reduce environmental uncertainty. So this is going to be the sort of guiding schematic of the talk. And so you have the feed-forward process of going from the microscopic level to the macroscopic, and then the individuals, there's no mystical downward causation here. The individuals, by reading off local or increasingly global properties, estimating those regularities, use those estimates to choose among their strategies to fine-tune their behavior, and that's where you get this so-called downward causation. So I just want to make this a little bit more concrete. Here's a brief video. You'll just see there are individuals moving around. In this case, some of the fish are going to form some amazing collective patterns, and that's the macroscopic. So from the individual behavior, just individuals moving around somewhat independently and then coming together to form these amazing three-dimensional structures. So not much correlation here. Predatory fish schooling. He's normally a great BBC voice. There you go. So there's some amazing aggregate level behavior. So that's the micro and macro problem. I'm arguing that a micro and macro problem is a collective computation, or we can think of it that way. So is that to say that life is a computer, or these fish, their social systems are kind of computing device? Well, not in this sort of strict sense, not in this literal sense, of course. Are we even saying that biological systems are circuits? No, but we're saying that there are some interesting ideas that we can borrow from theoretical computer science and modify in order to better understand how these outputs are produced in biological systems. So a simple standard computation from theoretical computer science would be something like this. This is the bubble sort algorithm. So you just have input, words, or lists, and array, outputs, an ordered list. You have this algorithm, and then you have a termination criterion, which basically says when it's the time to stop, when you've got the solution. Now, of course, this idea that biology computes, that biology is computation, is not new. This is a very famous schematic from the work of Eric Davis and his colleagues at Caltech. It's a gene regulatory circuit describing how the sea urchin, one simple aspect of the sea urchin's body plan, the specification position of cells in the endomesoderm is produced. So your input are genes and proteins. The circuit specifies the rules for coordinating these genes and proteins to produce this output. And it's amazingly complicated. Very rigorous. Again, these are determined in large engineering experiments. Say which genes turn on and off which other genes. But of course, there's all sorts of issues with this. It's an amazingly powerful framework. But if you're a biologist, you might say, well, the right output is not obvious a priori. How do we know which phenotypic trait to focus on? Which macroscopic property is actually an interesting one? There are many we can choose. And now, this is Boolean. How do we do with stochasticity and the role of context? These are modifications that need to be made to the sort of program coming from theoretical computer science to make the circuit computational picture useful in biology. And of course, if you're Boltzmann or a theoretical physicist, or even a theoretical biologist, you might look at this thing and say, well, that doesn't really help me understand how this output is produced. It's this really complicated map. It's like Bohr has mapped the world. It's not quite that complicated, because we don't have every rule in here. But we need some compression or compact encoding of this process that explains how we get this output, our theory. So where's the theory? All right, so what are basic elements of computation in biological and social systems, just to be a little bit more concrete? Well, the output is what's being computed. And an output can be, like I said, this simple thing like the position of cells. It can be the trajectory or volume of this bowl of fish. It can be something like the distribution of household incomes. And We say it's the output of a computation if it can take on values of the functional consequences of the group or component level. And this will all become clear as I go through my talk. It's the result of a distributed and coordinated sequence of component interactions under the operation of a strategy set. And it's a stable output of input values that converge to terminate biologically relevant time. So what's the input? Well, the input can be anything. It can be whatever you think is relevant to the output. So it does require a first sort of guess when you're building this framework. The actors or agents can be genes, proteins, neurons, individuals, depending on the output you've chosen. And they can have biological or social characteristics. Okay. The algorithm is not complicated. It's just a procedure or set of steps for mapping the set of inputs to that output in finite time. And the steps, as I'll be discussing, are going to be captured by circuits that describe how all of those strategies and decision-making rules combine to produce that output, that macroscopic property. Whether it's the trajectory of the fish school through space, or whether it's the distribution of income. Okay. Now that theory I was talking about is what we're calling algorithmic theory, a compressed encoding of the causal relationships that produce the output. That's what we are after in the long run. And it shouldn't just efficiently produce the output. We want it to mechanistically capture the computational logic of how the system, the actual biological system works. And so this is also from Eric Davison and his colleagues' work. This is a sub-circuit in that gene regulatory architecture that produces that aspect of the sea urchin's body plan. And it turns out that you can build these circuits for both sea urchins and starfish for echinoderms, they're closely related, and you find that there are certain sub-circuits, illustrated here, that are conserved. And so in the Eric Davison case, and he doesn't think about it this way as far as I know, but here the sort of compressed encoding is the identification, phylogenetic identification of conserved subcircuits that he calls, Doug Irwin call kernels. Okay, so that's one way of simplifying the circuits. There are other ways that I'll be talking about today. Okay, so what's our notion of correctness? This is the thing that we'll worry about least today. So we think that an effective termination criterion, and again, modification of these concepts to make them more useful in biology and maybe eventually actually make them more useful in computer science, can potentially be achieved if the system can create a separation of timescales between the aggregate level and the faster microscopic dynamics. The reason why that's important is because when you have this separation of timescales, it means that the aggregate property provides a sufficiently stable or slowly changing background against which the components can tune their strategies. So it's like a predictable environment. I know what the environment is. I may not love what it is, but at least I know what it is, and I can perfect my behavior in that environment. So there are a variety of ways we might construct these circuits. In the Eric Davison case, it's largely through experiment. We've introduced a set of tools that we call inductive game theory. And in inductive game theory, and for the game theorists in the room, this is motivated by game theory, but I won't talk about that today. The strategy and potential payoffs in game structure used by components are going to be extracted from highly resolved time series data. And we'll just go through that briefly. In these time series, we want to start with time series that would need to be non-independent and composed of interactions that are strategic. And then what we do is we take the stochastic circuit specifying how the strategies combine, we build these, and we test them in simulation to see if they produce our target outcomes, our macroscopic properties that we're interested in. Okay, and then we do this dimension reduction on the circuits to simplify them. So now I'm going to go through an example, and this comes from a model system that we use quite a bit to study these developmental questions, these computational questions in nature. It's a pigtail macaque group. In this case, it's a large captive group with about 50 mature animals, and we've got a time series on conflict dynamics that's made up of about 1,000 fights. It's a highly resolved time series. And the system's interesting. It's got what we call the minimum degree of relevant complexity. It's got social learning at the individual level. It's got multiple scales. It's got feedback. Individuals adapt their strategies based on their social structures and so forth. We know that from other work that we have other people have done. So it's a really nice model system for asking these kinds of questions. Okay, so the workflow that I'm going to go through for the rest of the talk is here. So we start with this rich microscopic data. We're going to choose a preliminary target macroscopic property that we believe, based on independent data, has functional consequences for the individuals in our system. So again, we're not just choosing any old aggregate level statistic. We're going to choose one that we think is meaningful for the system itself. We're going to identify our input, and we're going to define a strategy space in some principled way. Identify the strategies individuals might be using to produce this output, this social output. Then we're going to build these circuits, and they're going to be parameterized by the data, by those strategies we find evidence for. We're going to compress the circuits to try and identify the circuit logic and move toward this algorithmic theory. And then I will say a little at the end about how we might now take these reduced circuits and map them onto well-known frameworks in statistical mechanics like EEB models, so that we can harness the power of statistical mechanics, harness these well-understood models for studying properties or behavior of the system like criticality, sensitivity to perturbations, and other kinds of things. And you cannot do directly on the circuits themselves. But if we can show that there's a reasonable mapping from these circuits to something like certain kinds of EEB models, then we can harness that power of statistical mechanics. Okay, so what's being computed? So in the case, we work on a number of macroscopic properties in the system. The one I'll be talking about today is just this very simple distribution of fight sizes. That's all this is here. And we know that large fights cost individuals more. So as fight size goes up, the cost in terms of injury received that individuals receive increases as well. So this is going to be our target macroscopic property.
Sorry, is fight size the number of individuals involved, or?
Yeah, fight size is the number of individuals involved in each fight. So what causes fights to be of a certain size, and how do individuals decide to join a fight? Okay, so here's a typical fight in our monkey system. You see right away, it's not dyadic, it's triadic. One individual attacks another as a juvenile, third juvenile intervened on behalf of the first, and attack the female. So we've got a time series of fights like that. So here we have the total number is actually fight participants. The hours of the day, we start observations at noon, we go till 8 p.m. The bars tell you how many individuals were in each fight. The space between the bars is a equal period when there was no fighting going on. So this is essentially what our time series looks like, or our fight out time series. And what we have for each fight is quite a lot of information. The only information we'll be worried about today is who the participants were. So in this first fight, we have Fantasia, Taurus, and Thames. In this one, we have Yvonne and Zubrella, and so forth. So we have a vector of fight participants of size n, with ones and zeros, one being present, zero being absent. So we're asking this question: what causes fights to be of a certain size? How do individuals decide to join? So we're going to circumscribe a strategy space. Identify a set of strategies individuals could be using to make decisions to join. And since we're interested in the strategic interactions, these are going to be social strategies. So B decides to join the fight at t+1 because A was in the fight at t. Right. So we can write this down more generally in this way, C and M, that's just our notation. M individuals decide what to do in about t+1 based on the appearance of n individuals at time t. And we call this principle because we can actually write this down on a Markovian resource lattice, where one axis describes the coordination burden of each strategy, and the other axis describes the memory burden of each strategy. So just to break that down, a 1-1 strategy would be, I decided to fight at t+1 because, say, Dan was in the fight at time t. And another one would be, Pam and I fight at time t+1 because Dan was in the fight at time t. That's here. And as you go down this axis, the number of individuals who have to agree at time t+1 increases, hence the coordination burden. And as you go down this axis, the number of individuals that the individuals at t+1 have to remember in the previous time step increases, hence the memory burden. Okay. Now this goes on infinitely, right? So we have a huge space of strategies we could explore. Well, we don't want to explore them all. We don't have the computational time for that. And in addition, it's going to make sense. So we're going to restrict the space of strategies we explore based on what we know about the system. In this case, these monkeys are capable of dyadic and triadic interactions. We know that to be the case. Higher order interactions occasionally occur, but they're really rare. So we're going to restrict the space using information about what we know about their cognitive capacity to this small set of strategies. So we're going to look now in the data for evidence of those strategies. And I won't say in too much detail how we do that. I just want to give you a very coarse understanding. So again, here's our time series, our about time series. So these are the individuals, right? So we can look at this time series and see that, well, it looks like there might be some correlations. B is occurring at T, and E always seems to be occurring in the next fight. So we can rewrite our C&M rule strategies as these directed correlations. And we, of course, can ask, well, are those correlations, those directed correlations, causal? Are they really strategies? by testing them against a variety of null models to rule out other reasonable explanations. And we do that. We have a whole series of null models, some of which I have described here. And in the end, what we get are lists of all of these strategies, all of the pairwise and triadic strategies of that form, C11, C21, or C12, that we find evidence for in our system. So we have causality now at two levels, or we will. So far, strategy extraction. The cause of an individual or subgroup decision to fight, right? And in the case here, any number of these non-zero strategies, we just call it the significant above null ones, delta P's, for a given CNM is evidence for that strategy. So we just have these lists of all the strategies individuals play in these classes. Now in our model system, we find evidence for that in fact individuals do use all three types of strategies. But we find it very relatively small compared to the possible number, which is for each strategy quite large. And delta P tends to be small and the matrix is sparse for individuals who are interested in those kinds of facts. Now what we want to do is we extract strategies at the pairwise and triadic level. Next we want to construct these circuits. And we're asking, what's the cause of a macroscopic property? In other words, how do those strategies that individuals are using combine collectively to produce that output? So it's important to keep this in mind that we have these two senses of causality, two levels. Okay. So our goal is to capture configurations of strategies that produce this output. And we're going to build a circuit now for each CNM strategy class, right, for which we have evidence of significant strategies in the data set. So the first one, the edge is simply C11, A induces B at, this is the delta P value, say at 0.05. Here AB induces C, A induces B, C, right? So these are going to be edges in our circuit, or edges in our network, and they're going to be weighted by the delta P, by the probability that A induces B and so forth. Essentially, it's a probability. And the edges will be generative or inhibitory, depending whether the weight is positive or negative. So in some cases, you can inhibit, like Dan could inhibit you from fighting that. So we can extract that from the data as well. And so what we do is we build these circuits. This is the circuit for the C11 case. Probability that B is induced by A, above null probability. And here, again, just to be clear, so here's Zubarella. And in this individual, BF fights at T+1 if Zubarella appeared in the fight at time 2, the previous fight. So an arrow indicates that the sender is inducing the recipient. The dashed arrow indicates an inhibitory relationship. We don't quite have a circuit yet. So again, at the edge level, we've got causality, the strategies, and then the combination of these strategies is the causality producing the output. So here's the C21 circuit. AB goes to C. And here's a little different kind of circuit because it's bipartite essentially. So you've got, this animal Cody is bites at time T+1 if she and udder fought at time 2. And the dashed lines similarly are inhibitory. So this is just a subset of the full graph. It's got many thousands of edges and nodes. And one thing that's important to notice for both of these circuits, for both of these networks, is that the individuals can have many triggers, or they can have multiple strategies that may turn out to be in conflict. So let's just break this down a little bit. So how do we actually combine these potentially competing strategies to produce a circuit? So consider the C21 strategy space. So delta P is positive. Probability has a positive probability AB tells C to join the next fight. You can think about it that way. Or the probability that AB tells C to avoid the next fight. Now in many fights, the fights in the system range from 2 to 30 animals. They can get quite big, although the bigger fights are fairly rare. There are more individuals than just A and B. So what if E tells C to avoid the next fight? How does C know how to proceed? Well, C has to choose between the recommendations of A, B, and D. So we introduce a combinator or a Boolean operator, and there are two variations. The OR gate is a kind of conflict-prone one, and it just means that if anyone in the set that you respond to, for whom your strategy says go, you go. And the AND gate is more conservative. It's kind of like a conflict-averse mechanism. And here, the idea is that everyone has to agree that you should go. Okay? So these are just two simple mechanisms to capture the space of the problem. There are many variations you could pursue, but we want to keep things as simple as possible. Okay. So now what this gives us is a family of stochastic social circuits, with each circuit serving as an alternative hypothesis for the output. So we've got the C11 and the C11 OR, and so forth. Now the circuits are parameterized by the data insofar as all of those edges, the weights on those edges, come from the data. There are those strategies and the probabilities associated with the strategies that we extracted from the data using those null models. And what we're going to do is take these circuits that are parameterized by the data, run each forward in simulation. So we're going to let them compute solutions, distribution of fight size solutions, and see which distribution that each circuit computes, whether it can recover the observed distribution of fight sizes. So this looks a little complicated. It's quite simple, really. This is the data. You remember that slide from earlier in the talk. This is the C11 and OR result. So as you can see, C11 just generates for fairly small fights. And again, it's important to remember, these are the simulations of circuits as they perform as parameterized by the data. This is C12, so you see it generates many large and many small fights, so it's capable of producing these forest fires. C21 OR also does that. And C21N recovers the data by far the best. Of course, we do all sorts of model selections to evaluate these fits. Now we predict fine grain statistics as well as these forest ones, and we comment into that. And the reason why we think C21 doesn't recover the tail so well is because one of two reasons. Either large fights are actually quite rare, so there's a lot of noise in the data. And also we think that when you get to large fights, individuals are using a combination of these strategies. And we're remember testing each of these circuits independently. So the circuit that, our best performing circuit is the C21 circuit. So now what do we have? We've got these complicated circuits. If you recall, I was criticizing softly, I think it's great work, this Eric Davison deregulatory network because it's so complicated and we can't do much with it. It's a very rigorous description of how you go from the genes to the output to the seems to be a feature, but I can't say anything general about it. We have the same problem, of course, with our circuits, right? These are these amazingly complicated circuits with many nodes and the edges have weights on them. And so what can we say about this? What can we learn about this process just by looking at these circuits? So we need to do some dimension reduction on our circuits to make them simpler. We want to build that algorithmic theory that sort of compactly describes this mapping. And as I said in the Eric Davison case, he does that by looking phylogenetically for these conserved subcircuits. But there's another set of approaches that we might take if we're not interested in a phylogenetic perspective or not comparing the evolution and development of body plans. And before I introduce those, let me just say that we want our theory, one of the things that motivates us in doing this work is we want to understand how nature computes. We want to understand how nature computes given the cognitive capacity and constraints that the system itself faces. The cognitive capacity or the computational capacity of these components. So our theory should be computationally or cognitively principled. We don't just want an efficient theory that can predict the outcome. So we want to capture how the components who have their own theories, and even this is true even for not for simple things like genes and proteins, neurons, maybe with a slightly more formal language, but how the components themselves, given their theories of how the world works, the data they have access to for making decisions, how that process produces their behavior and how then their behavior based on that noisy process combines to produce these collective outputs. Okay, so we can go back to the raw data and we can say, well, we could coarse grain this raw data. We could, instead of using all the individual information, so we think our input, we could coarse grain the data and ask, well, maybe we divide our individuals into males and females, or we use some biological or social information to coarse grain our individuals into groups. That's one approach. We work a little bit on that. Another approach that we've explored is, well, look at that time series. There's a lot of noise in that time series, and there's a lot of redundancy in there. Can we compress the time series before we do any analysis of it and find predictable and regular subgroups and individuals? And then ask, remake the circuits, and then ask whether the individuals have strategies to these regular and predictable individuals and subgroups. And you can, this makes some sense because you can imagine that it would be very hard to build a strategy for individuals unpredictable. So why not just ask about strategies for the individuals we know are behaving predictably? Now I will talk a little bit about how we might go about doing that in just a second. And we can also coarse grain the circuit itself, doing much the same thing that we did to the time series, rewrite the circuit by grouping together individuals that share similar biological and social properties. Or we can, other things that we are considering is extracting the edges in a different way, using direct information and some other approaches to get a smaller, more robust set of edges. So just quickly, how could we compress the data, the original time series, to do this dimension reduction? Well, one approach comes from neuroscience. It's called sparse coding. And essentially the idea is to find those regular and predictable groups. The sparse coding algorithm represents a given set of bytes using combinations of basis vectors with this constraint of sparsity. And the vectors are found by minimizing a cost function that makes the trade-off between accurate representation of the data and the sparseness of the fit coefficient. So in the equation, there's a reconstruction error rate and a sparseness penalty. And what comes out of this process is sets of individuals and subgroups that are regular and predictable. So that's represented here. So for example, we see that sassafras, dark, and ocean are a group, and they always occur together according to the sparse coding algorithm. Not always, almost always. And here, let's see, we have quite a big one. Fortune, Earth, Ovo, Quest, Eocene, and EEB are highly correlated and very predictable. So we get back these sets of individuals and subgroups that VF individual, right, who show this more comprehensible behavior. And now what we do is we perform the inductive game theory circuit construction again using this information to restrict the strategies we look for. So this is just two examples of circuits in our sparse circuit family. They're still stochastic. We've got here, this is the more interesting one, we ask here, any individual, whether predictable or regular, what strategy does it have for the predictable and regular individuals? Can we find evidence for those strategies? And we draw the circuit. So in other words, Lori here has a strategy for this predictable group, Zubarella, High Point, and B occurring in the set just prior. And here we just draw the circuits. We just allow only the predictable and regular individuals to have strategies. We just look for those strategies in the data. Okay, and I won't, that's work in progress, and I won't show you the fit to the long fraction to the distribution of byte sizes. But it is reasonable. It's not as good as we would like yet, and we think there are a variety of reasons for that. It has to do with noise. But one of the questions we might ask is, okay, well, we're interested in a cognitively principled collective computation. So are we really legitimate in going to the sparse coding approach? Isn't that computationally quite intensive? Doesn't it assume that the monkeys are, performing this algorithm, and how could they possibly be doing sparse coding? Well, I'm not saying they are doing sparse coding, but we can start to ask principled questions about this by asking how the sparse coding algorithm compares to other types of models that one might make in terms of the number of bits, the entropy, that's required to store each model's parameterization of the data. So this is a way, a first pass, that is trying to quantify the computation, the cognitive burden of using a particular algorithm or model to do these collective computations. And so what you see in this plot is to make some proportion of correct predictions of statistics in the data, how many bits are required by each type of model in order to make those correct predictions. And what we see is that sparse coding requires on the order of 1,000 bits, and it's fewer than a frequency model or a spin glass model or the random model. Right? So the cognitive burden of the sparse coding model is actually less by this measure than of these other models that might be implied. And that actually don't recover the long fraction as well, but are simpler models by some estimates. So far, we are working slowly, and there are other ways that we do this besides sparse coding, but we have that here for the moment. We're working slowly to building this algorithmic theory, this mapping, to compress this mapping between micro and macro. And just to come full circle back to the beginning of the talk, directly compared to Eric Davison, we've got our microscopic description. We're trying to figure out the extract from the data the microscopic behavior of the system. And not just any behavior, but the strategic behavior. I think that's very important in biological systems. In physics, you might just describe the velocity and position of particles. Here, we can't just describe behavior, we think we need the strategies. So you want a nice, rigorous description of the microscopic behavior, and we can get that using inductive game theory. Then we identify a provisional output, one that we know has functional consequences, and we try to build a compressed description of this mapping that's cognitively principled. And in the Eric Davison case, his rigorous microscopic description comes from experiments. He does these phylogenetic comparisons, and that's how he gets his sort of theory for the output. Okay, the nice thing about this inductive game theory approach, the circuit approach, is that it gives us the natural scales of the system as an outcome of the analysis. And oftentimes in biology, we are imposing scales on our work. We're looking down at our systems and we're saying, that's the individual, that's the mesoscopic, that's the macroscopic. Really what we should be doing is letting the data tell us what those scales are. And if you use this approach, the scales fall out. So now, just a few more minutes on macroscopic tuning and control. So let's come back to this result of our simulation. And one of the interesting things about it is it tells us, as I said, which strategies and circuits seem to be the right circuit for our system and the macroscopic property that we're interested in. It also tells us what the distribution of fight sizes the output would look like if another strategy was being played with those parameters in our system, right? So we know that if the monkeys in our social group were using the C11, we'd have a lot of short fights. We know that if the monkeys were using the C12 OR, in fact, there'd be these huge forest fires. And if you're a biologist or you work with primates, you might immediately be thinking to yourself, well, in fact, I know that the macaque genus is incredibly diverse. It's got 20 or so species. They have very different social structures. There are some quite despotic monkey groups, and there are some in the middle, like the pigtails and the stumptails, that have this kind of like policing mechanism, and then there are these egalitarian ones. Is there some way to understand? They're all doing the same thing. They all have interactions and dominance relationships. Is there some way to understand how we can push one system into another state? How can we move between these macroscopic descriptions, these different types of social structures? Right, and so you could ask, as a sort of first pass at that, well, how can I perturb the distribution of fight sizes to change it so that it's no longer like this, but we've got a distribution with many small fights? Very different system. That might be more research-like. So how can we ask that kind of question in a rigorous, principled way? How can we study these transitions between potentially neighboring accessible states at the macroscopic level? So we want to introduce a kind of control parameter where we intervene on ideally the algorithmic theory, or in the absence of a good algorithmic theory, directly on the microscopic behavior, to see if we can induce S1 to become S2. Now what that really requires, as I said, or alluded to at the beginning of the talk, is drawing on well-understood modeling frameworks from statistical mechanics, where the model's behavior is understood, well-known for these many-body systems like these. And in biology, there's a long tradition of importing Ising models and other frameworks without the microscopic data. So what you typically do is you see some coarse variable, some distribution of fight sizes, for example. You don't have the microscopic description, so you impose some simple model on the system because it's a good null, it's a good approximation in the absence of that data. But now biology has this problem is that the microscopic data are coming in. We are starting to understand what the real microscopic interactions are, and we can no longer just jump directly to this kind of simple modeling framework that makes very simple assumptions about the nature of the interactions. We need to be able to map, if we want to use those modeling frameworks, map our circuits, our microscopic descriptions of the interactions to those models so that we know we're justified in going there. And so I've just got that represented here. So here's like our circuit from our monkey group. The edges are directed, causal edges and the weights are parameterized by the data. And we can ask, this is fairly close to the true microscopic description. Right? There's other behavior we haven't captured in here, but it's very close to the data. It comes directly from it. We're making very few assumptions. Here we've got directed causal edges, compressed or coarse grain variant, our algorithmic theory. So this is our sparse reconstruction, our sparse circuit. Now, when you have this sort of undirected edges, and the weights are correlations from the data, this is like an Ising model. Okay? And it's close, it's relatively close to the data because you're using the correlations in the data. And here you have the same thing, but you have, say, for example, a uniform distribution of edge weights. So it just gives us a sense of the distance from the original data or the true data, the microscopic data. And we want to test, you could say, well, okay, just apply these different models to run them forward in simulation and see which works best. That's the sort of standard thing to do in biology, usually, here, in the absence of any information, microscopic information. But that's not really good enough, and so we're worrying a lot about when you can do this mapping. And we'll talk about that today. We're trying to understand what this sort of formal relationship is between these simplifications here, and our data. When is one of these models actually a reasonable approximation? Is what we're asking. The reason why that's important is you can, as I said, do quite a lot with them if you feel justified in that representation of your data. And just to give you a sense, one of the things we're exploring now is, just about finished with this work, is where our system sits with respect to the critical point. And the critical point is just the point at which the system is sensitive to perturbation, so that a small fluctuation at the microscopic level can induce a large-scale change. Okay? And what we've got here is, again, for our fight size data, we find this is the susceptibility or the sensitivity of average fight size to this external perturbation, and the external fields are control parameter. And we find that this peak, all that you need to know about this slide is that the peak indicates that our system, which is finite, and there's a lot of issues there that we can talk about if you're interested. Although I don't want to say too much about that at this point, is near a critical point. And what that means, critical point is one of those things, again, in biology, which can be interpreted in many different ways. It's good to sit near a critical point. You'll hear some people say, because it means that rapid change is possible, the system can innovate. It's bad to sit near a critical point because that means a lack of robustness. So there are many just those stories that one could create to talk about the critical point. But it is the case that we are finding, this is based on the work of Bill Bialik and some other folks, that many biological systems do seem to sit near a critical point. Turns out, what we're discovering is how close you sit is what matters. And so our recent work, we find that the critical thing, or the important thing rather, is that the system can tune its proximity to the critical point. And that way it can adjust its behavior depending on whether the environment changes, whether large-scale change is likely to be a good idea. Okay, so, and in addition to that, I'll sort of end by saying that we have a relatively simple mechanism that can control this distance from the critical point. So one of the things that's also not well understood is how the system comes to sit near a critical point. And the nice thing about a critical point is that it means that you don't have to control many small parameters, right? But there's not much understanding of what gets a system there. And there's some indication that, in fact, the systems sit near the critical point as a result of trivial stochastic processes. And it's actually sitting away from the critical point that's interesting in biology. So it's just a fascinating series of issues here. But what we're essentially after is understanding these control mechanisms so that we can see if we can induce and understand the logic that takes you from one macroscopic state to another. And then, of course, I mean, this is quite grand. I'm just speculating, playing around here. But what we sort of want to move towards is a kind of thermodynamics of biology. Can we ask, once we have these mappings, what are actually the relationships between these different macroscopic properties? So I'll talk a little bit more about this tomorrow. So in biology, we have some well-known macroscopic variables like mass and from scaling work like metabolic rate and mass. Macroscopic variables, we understand the relationship. They scale in most biological systems at the 3/4 power. In systems where we seem to have these macroscopic variables, and we understand the relationships between them, we seem to be talking about energetic issues. When we're talking about social systems where the macroscopic variables are more informational in character, we haven't been as successful in identifying these macroscopic properties and what their relationships are to each other. So our research program is in part, we're arguing that by understanding this mapping, this construction or computational process, and building these compact representations, it's that way that we're going to understand, we're going to be able to identify the critical or important macroscopic variables. And once we have them, we can ask what their relationship is to one another. So in physics, it proceeded the other way. We did the observations at the aggregate level first, and then tried to derive them from from statistical mechanics. And I'm suggesting that because of this informational quality of biology, we may have to do it this way. And once we understand these mappings, we will be able to ask how the long fracture distribution of fight sizes relates to something like one of the other variables we studied, the distribution of power in these groups. So I think that's the end. Yep, that's my final slide. So thank you all for listening. I hope that you found something in there interesting.
I have a question. So, fish and schooling fish, you might expect to have, you might not expect, but you might initially expect sort of aggregation fish. They don't have long histories of relationships in contrast to the macaques. Does the nature of the possibility of set of relationships and knowledge of those relationships put an upper limit on the complexity of the nature of the rules that will emerge? And if so, then just because you can have complex doesn't mean you will have complex. So if you're with 1,000 fish, but you have very simple rules that lead to a school, that's very different than the possible set of all possibilities that diamond matrix you had for the macaques. But that's got to be costly to have much more complex rules if you're a macaque. It's based on a lot of knowledge of others.
Right, so I think that's a very good question. I think we don't understand the relationship yet between complexity at the rule level and complexity at the social structure level. So here we have that, I think this is what you're referring to, right? So we have to draw something like this for the fish. And I presume the coordination, because we started this at the C11, and presumably the fish probably aren't doing anything more elaborate than something like a C11. I mean, they're they are attending to the behavior of their topological neighbors. And so I think the rules are probably fairly simple. Now we do see that the neighbors that they can produce at the aggregate level are incredibly beautiful. The extent to which they're complex, I think to answer that question we have to start asking how decomposable is that collective behavior?
Can you find simpler rules being used when you put a bunch of macaques together as opposed to more established groups? Because they don't have that lookup table, they don't have those relationships understood, it's not possible in a more complex way.
So I think that if you were to put a group together without that, didn't have that experience to build on, they wouldn't really have social strategies yet, or they'd be very poor strategies. They'd be strategies for large animals, strategies for males, they wouldn't be strategies for specific individuals. So that comes back to the course being pointers.
Yep.
And I also think that your delicate edges, the weights on it would be very small, really tiny, a lot of noise. But you could watch it. Yeah, so I think we, again, so there's a many one mapping between the microscopic configurations and the microscopic output. And that's one of the reasons why I think having good measurements in the microscopic is so important. There are many models of that, many circuits that could predict that output, right? And so you need to make those measurements on your data. And whether, the complexity of the rules affects the complexity of the aggregate structure, I think that's really an open question. Not all obvious to catch.
When we try to apply the rules in bird songs, we sometimes find that they're not all homogeneous in time. That later in the season, the birds are doing different things.
Yeah.
Early on. And I would imagine some of the cats or nestis or have other people here doing things that are not on the cats do. But they can usually be using different rules at different times.
Yeah, so that's the context dependence that I mentioned at the beginning of the talk. And so remember, the strategy is a kind of decision-making. I mean, the very notion of a rule is kind of average, right? So it's true that there are going to be all these contextual factors, but unless there's some regularity to those contextual factors, individuals won't be able to build a strategy response. Now, if there is, then it's just like, well, when I'm in estrus over the summer, whenever it is, I behave this way. There's a concerted rule for that context. And then when I'm not, I behave this way, another rule, right? We would be able to capture that. But for all of this, all of the noise in the system, just like fluctuations that don't have any, that's just going to be, that's just non-strategic noise that we can model.
There are principled ways to see whether a Markov process is homogeneous or not. There are principled ways of seeing whether the strategies that you're identifying are homogeneous.
So we do look, so this is, of course, we construct these strategies using the entire data set. And we really don't even have, I mean, it would be nice to have much more data. I'll come back to that in a minute. It's not as easy as that. It's actually tricky because the system evolves. And so if you have more data, it's not necessarily better because you might be capturing a lot of that, right, transit behavior. So we have this problem of restricting the amount of data that we allow, given how fast we think the system is changing. But when we do look at the day level, and we do see variation in our delta P's and in the probabilities associated with our strategies. But it's very hard because at the day level there is very little data, on the order of 60 fights. So it's very hard to know whether those delta P's are different because they're noisy or because, in fact, individuals are refining their strategies through learning. But we have a number of papers where we're exploring this from a modeling point of view, where we ask, like, what's the time to strategy, or what's the time to decision, or the time to signal based on what we know about the system. And so we're trying to get a sense of what role learning plays in getting the delta P's and probability of the strategies to consolidate. But it's true, there's non-stationarity in there, and that's one of the things. It's actually one of the reasons why we were motivated to move to this inductive game theory. And there's just, the assumptions in game theory, stationarity is a big deal, and the world isn't stationary, and we think a lot of the interesting structure comes from transits. So we want to be able to measure and quantify it. But yeah, we'll see the challenges there.
I'm struck by what you seem to be talking about from my perspective. There's a bunch of emergent properties of the collective behavior, and these emergent properties apply probably across the board to all sorts of things like fish schooling and these interactions you were talking here. How close do you think the thermodynamic analogy is with respect to this? Because when I was an undergraduate, I took a course in statistics and mechanics and figured out there's a real connection between physics and thermodynamics. And I teach physiology, and physiology is applied thermodynamics. And that's what this sounds like to me. And you use the term entropy. You also have a concept of free energy, and things related to that.
So for us, emergence, I mean, our sort of working definition of emergence at the moment is that there's a construction of this new, in biology, of a new time scale, slower time scale. And I'll talk a little bit about this tomorrow. And there's some surprise or uncertainty reduction. And so the distribution of the fight test distribution is not emergent, but or the power distribution, which I'll talk about tomorrow. But it makes accessible new social functions that were not accessible under other distributions, and that's the emergence. It's this surprise or uncertainty reduction. In this particular case, for this system, the distribution of power makes possible a new conflict management strategy called policing. That was not accessible before. So that's the emergence. And so we are trying to understand that process of biology. And we think it has to do with the slow time scale, the uncertainty reduction. Some people say a phase transition, or I'm not sure that's essential. But they're definitely, we're using statistical mechanics to ask those
There's
questions.
certainly a lot of formal relationships or formal similarities.
Well, even in physics, I think emergence isn't fully understood, right?
Okay, so question about sort of the goal of the group, the objective of what the group behavior is supposed to accomplish. So if you're looking at a fish school, and if the objective is to swim efficiently from one place to another, then everyone in the group has the same goal, which is to minimize energy, and the school can be hydrodynamically oriented that maximizes both the individual and the group. But when you put the fish balls up, the response to a predator, what each fish is trying to do is to avoid being eaten. And what happens is that they all become more vulnerable to being eaten because they all dive to the center of the school and they form a ball, which predators have free lunch. So how do your models sort of deal with this? It seems to be very different goals. And one goal, the group result, is actually bad for all the individuals, whereas everyone's trying to maximize. And the other one is it's good for all the individuals, but it's the same thing. The individuals are trying to maximize their individual benefit.
Well, the fish ball case is complicated because the ball does allow individuals who can get into the center safety. structure does. But it's true that it makes it, from the predator's point of view, to swim through and gobble, 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 right? But it's a way of hiding, essentially. So it's not clear, and you must be very careful of understanding. I think there's a lot of costs and benefits in this collective computation that are being traded off against each other, and the output is this thing. And it's not easy to look at. You can't easily look at the thing and say it's good or bad. You have to understand all of those trade-offs and how they're being made in order. That's what the collective computation is. And so an easier example to understand is actually the distribution of power I'll be talking about tomorrow. So there, you get these heavy-tailed distributions of power. We can show that they support these special third-party conflict management mechanisms like policing. And the effect of policing is to reduce the level of aggression in the group. Individuals will often pay a lot for, they're at the bottom of the power structure, pay a lot for aggression, redirect aggression. They benefit, everyone benefits, but some individuals' behavior, some individuals who benefit a lot from fighting unchecked, they're obviously paying a cost. And the question, so that, on average, I think it benefits everybody to have this policing mechanism, but there are individuals will try and sort of circumvent the policing mechanism so they can fight, right? So there's constantly this struggle. And you have to ask the question, so in the social evolution literature, the models of policing for a long time, like all models of cooperative behavior, assume that the problem was hard because why would you pay to police if, by policing you have to approach the conflict, it's costly to approach the conflict, you redirect aggression, et cetera, et cetera. But it turns out that if you build this heavy tail distribution of power, the individuals who are in the tail are so disproportionately powerful that they're never challenged in response to their policing interventions. They play negligible to zero cost. And the question is, why do you get this heavy tail distribution of power? And how is that leading to this new function, this policing? And the way it works is that the individuals at the pairwise level have this history of fighting with each other, and one individual is learning, the one that ends up sending this thing called the subordination signal, that is the weaker animal. And it's in its benefit to agree to be the subordinate in the relationship, because by being subordinate, it gets certain things that it wouldn't get if they didn't have a relationship like that. And it can't win, right? So the optimization is occurring at the pairwise level. And then the signaling optimization, this agreement about status. And then in the network is encoded the distribution of power. So if you look over the whole network of these signaling interactions that tell you about subordination, you find out what the distribution of power is, and you can in fact predict from that things you should predict if it is actually a distribution of power that's encoded in this network. And so the basic story is that because of pairwise optimization, pairwise trade-offs and cost and benefits agreeing to this dominance relationship, you get this heavy tail distribution of power. That's the collective computation in this case, right? You get a distribution of power that allows for this special policing mechanism that further slows down the social interactions and further stabilizes those dominance relationships.
So are you saying then if you understood the microscopic behavior, then the group dynamic just falls out always?
I'm saying, yes, in part I'm saying that, but the whole question is, how do these systems find those solutions, right? Because the collective behavior, the power distribution, if you want to induce a change, so you have moved from a normal to a heavy tail distribution, what is required for that to happen? And what I want to understand are those steps, the logic of those steps, and how, given that this is a collective system, what needs to be perturbed? Can you perturb single individuals? Do you have to perturb subgroups of individuals? How do you intervene in the system to efficiently induce a change? And how can that evolve? How can that sort of mechanism evolve?
And with that,